I've gotten you excited about generative adversarial networks. We've gone over the prerequisite theory from my previous live lessons. Now it's time to just go over at a high level the essential theory of generative adversarial networks so that when we start writing our code in a moment, we know why we're writing the code that way. So at a high level, generative adversarial networks pit two deep learning networks against each other as adversaries. One of these networks is tasked with generating novel images, while the adversary, the discriminator, critiques these images, attempting to discriminate the real from the fake. So we can kind of think of the generator as a forger that's like forging fake paintings, and the detective that's tasked with discriminating these fake forgeries from the real thing from the museum, you know? So these images, these real images, could be photographs, they could be drawings, they could be paintings, and over time, by training this network, and I'll get into the detail a little bit of how that happens in a moment, we go from the network initially creating random noise, generating random noise, to generating compelling synthetic machine-generated analogs to whatever the real images we were putting in. So these can end up being stunning photorealistic images with flexible user-specifiable features, and in general, generative adversarial networks offer many of the most surprising advances in deep learning in recent years. I provided you guys with lots of good papers for following up on the detailed theory of this approach earlier in these live lessons. For more detail on the mathematics specifically, if my high-level intro here isn't enough for you, check out the Goodfellow, Bengio, and Kerrville deep learning textbook. So let's go over in a little more detail what's happening here. So let's talk about the discriminator first. You can think of the discriminator's task as like a classic supervised learning problem. We're feeding it real data labeled with ones and fake data labeled with zeros. And we're training it to become better at distinguishing the reals, the ones, from the fakes, the zeros. So let's say you typically start it with a 50-50 split. So 50% of the images going in are real, 50% of them are fake. They're labeled appropriately as real or fake. And this discriminator, which consists primarily of convolutional neural networks, as is common in machine vision, it's scanning the image for features that are characteristic, that indicate that this is real versus this is fake. And over time, these guesses become better and better because we feed back with the cost function, we get an assessment of how wrong the guesses are, and then using, with the cost functions, we get an assessment of how wrong the guesses are, and then we use gradient descent to take steps in the direction of minimizing the cost so that we're more often guessing that real images are real and fake images are fake. So that's this loop right here. Now, we alternate that loop, that training of the discriminator, with training of the generator. So after one iteration of training the discriminator, we freeze the discriminator's weights. And then we pass information into the generator, so a starting point, a kind of seed for what image the generator should create. So remember, when it starts, this generator is pretty much just creating, gray images because its weights and biases are randomly initialized. But over time, this generator will start to generate compelling images. I'll get into how that works in a second. But when it's actually working properly, it's kind of relevant what we feed into the generator. So if we just feed in random noise, so let's say we have a 100-dimensional latent space, then our noise would just be 100 random values. So we'd be specifying a random coordinate in the latent space. And then this generator would just be creating a random image from the latent space of possible images that it can create. Alternatively, we could feed in specific latent space coordinates because we're looking for a particular kind of image. So, a particular kind of celebrity's face, one with a beard and glasses or whatever. We know kind of in general, once this is well trained, you can map the latent space and have a sense of what to expect. You can do latent space arithmetic, like I showed you earlier in these live lessons, to come out with a specific coordinate that you want to specify for the generator. Or you can combine both. You can have a specific coordinate that you roughly want the generator to produce some output from, and then add noise to it. Anyway, that's for later on once you have your network well trained. When you're starting off, or when you're training your network, you're just feeding in noise into the generator, and this generator, this forger, consists largely of D-convolutional neural networks. So this is perhaps the first time you've ever heard of these D-convolutional networks. These are the inverse of a convolutional neural network. So the convolutional neural network is scanning images to look for features, and then the neurons of the convolutional neural network, the filters, come to represent particular features regardless of where they occur in the image. So, the beak of a bird, or the face of a dog, an eyebrow, whatever, becomes represented by the various convolutional neural network filters. The deconvolutional neural network is the opposite. So it starts with that filter representation, the dog's face or the eyebrow or whatever, and then it places it onto, in the case of a black and white image, a two-dimensional shape, or in the case of a color image, a three-dimensional object. Okay, so deconvolutional neural networks are the name of the game here in the generator. And this generator generates fakes. Now what I said was, after one iteration of the discriminator, discriminating real from fake, where we minimize the cost of these real to fake labels, and then, so we train these weights, then we freeze those weights, and we alternate that with noise being pumped into the generator, fakes being produced by the generator, but critically, we don't label them as fake, we label them as real. And so then we have this other parameter tuning step where we're tuning the generator. So the discriminator weights are frozen, we pass in fake images, label them as real, and then ask the generator to minimize the cost between these fake images being input, labeled as real, and so we're constantly shrinking. We're using the cost function and the gradient descent to shrink the difference between these fake images that we're labeling as real. So the generative adversarial network is this continuous loop of 50-50 real and fake images being passed into the discriminator, us minimizing the cost of the real versus fake, training the weights of the discriminator, then freezing those weights, and passing only fake images through the discriminator that are labeled as real, and tuning the generator. So these are the two key steps. We're going to go over this again as we go through the code, and when you can see it there, this might make even more sense. But hopefully this provides a good sense of overall what we're trying to do and get out of the code that we're about to write.